In a previous video, we examined the basic principles of Ohm's law in a single path or series circuit, using a water analogue as an example. Now we will focus on multiple path or parallel circuits, using the same water analogy to illustrate their characteristics. Water pressure from the pump is associated with voltage. The liquid's flow rate in the circuit represents current, and the restriction in the pipes simulates electrical resistance. As in our previous video, we will demonstrate the water circuit and its electrical equivalent and compare the observed findings. The water pump represents the power supply, and a large plastic tube represents circuit conductors. Taps in the circuit simulate switches, and smaller plastic tubes represent circuit resistors. In a series circuit, resistive elements are placed in succession, like train carriages, as previously shown. A parallel circuit places resistive elements next to each other in the circuit. In this configuration, the same pressure is applied to each resistive element in the circuit, and the flow in each resistive component is now determined by its resistive value. Now, let's look at our water circuit. With one element in the circuit, the flow rate is determined by that one component. The lower the restriction, the greater the flow. We see the same response in the equivalent electric circuit. When we add a second element, we notice an increase in the overall flow rate, because there are now two flow paths for the current to follow. This is also seen in the electrical circuit. As more parallel elements are added to the circuit, the overall opposition to flow reduces, given that each path added allows some flow to take place in that path. For example, if we take two identical restrictions or resistors and place them in a circuit in parallel, the flow rate in the circuit is double that of a single restrictive unit. So the supply sees a total resistance of half the value of each restriction. When further elements are added in parallel, opposition to flow reduces even more. This proves the statement associated with Ohm's law, which says, in a parallel resistor combination, the overall resistance will be less than the lowest individual resistance in the combination. From Ohm's law, if we know the applied voltage and the resistance, we can work out the current in any resistor. If we have a 10 ohm resistor connected to a 10 volt supply, it will draw 1 amp of current. Two of these resistors in parallel will draw 1 amp each. When 2 amps flows in a circuit with 10 volts applied, Ohm's law determines the circuit resistance, which is calculated at 5 ohms. A third resistor of 10 ohms added in parallel will reduce the overall circuit resistance to 3.33 ohms. In a series circuit, the addition of resistive components increases total circuit resistance. Here, the opposite occurs. The more resistors inserted in parallel, the lower the overall circuit resistance. In a series circuit, an open circuit resistor will cause the circuit current to stop. In a parallel circuit, an open circuit resistor will cause a resistance rise and current drop. Where total resistance in a series circuit is the sum of the individual resistive elements, the parallel circuit is different. Total resistance here is the reciprocal of the reciprocal sum of the individual resistance values. To find a number's reciprocal value, we divide it into 1. Most calculators have a reciprocal function key. Looking at the three resistors from the previous video, 12, 15 and 22 ohms, placed in series, we have a total resistance of 49 ohms. With an applied voltage of 10 volts, the circuit will have approximately 200 milliamps of current flowing. The same resistors placed in parallel give a total resistance of 5.11 ohms. And at 10 volts, the circuit has almost 2 amps flowing. Let's look at the calculation for each circuit, using the identical three resistors in both cases. We note that in the series connected circuit, the supply delivers current based on 49 ohms of resistance. The parallel circuit, using the identical three resistors, produces a load of 5.11 ohms. The calculations align with the observed operation in our analogue and the electric circuits, proving the outline principles of both circuit configurations. Next, As the final part of the Ohm's Law series, we will investigate combination circuits with both series and parallel elements.